You ever stop and think about the welds holding together, say, a bridge you're driving over, or maybe the pipelines that bring energy to your home? They are literally the hidden stitches holding our world together. But what happens if one of those stitches is flawed? Let's dive into how we make absolutely sure they never, ever fail.
Right, there's the big question, isn't it? We're talking about finding a tiny little crack, maybe an imperfection buried deep inside a thick piece of solid steel, a flaw that could lead to a total disaster. How in the world do you find something like that?
And, the stakes here could not be higher. A single, invisible flaw in a critical weld. Think a power plant, an airplane, a skyscraper. That's not just a defect. Nope, that is a potential catastrophe just waiting for its moment. So making sure those welds are perfect isn't just important, it's completely non-negotiable.
So, in this explainer, we're going to pull back the curtain on the incredible tech and the super strict processes that keep these welds safe. We'll start by looking inside solid steel. Then we'll get into the rulebook that governs everything. After that, we'll cover the pre-flight checklist for every scan, the scanning process itself, and finally, how the final call on a weld's safety is actually made.
Okay, so how do you solve a problem like seeing the invisible? Well, you use technology that can literally peer inside solid metal. Let's meet the hero of our story. It's called full matrix capture, or FMC for short.
The easiest way to think about it is like a medical ultrasound, but for a piece of steel. FMC blasts sound waves into the metal, but here's the magic trick. It captures every single echo from every possible angle. This creates a massive amount of data that software then uses to build this incredibly detailed, almost video-like image of what's going on deep inside that weld.
Now, don't worry about the fine print here. The whole process really boils down to 3 simple steps. First, the inspector defines all the settings for the specific weld they're looking at. Then, the machine gets to work, acquiring all that raw ultrasonic data. That's the full matrix. And finally, some really smart software takes all that raw data and reconstructs it into a crystal clear image, letting us see any flaws that might be hiding in there.
And this is really the key difference. A conventional ultrasound gives you like a single snapshot from one angle. It's easy to miss things. But full matrix capture, because it collects so much data from all these different angles, it's like getting a full motion video of the weld's interior. It is an absolute game changer for accuracy.
Okay, but having this incredibly powerful technology is only half the story. I mean, how do you make sure that every single inspection done by any person at any company anywhere in the world is done to the exact same high standard? You need a rulebook, a serious one. And that's exactly where something called the ASME Boiler and Pressure Vessel Code comes in. This is the universal playbook for these kinds of inspections. It's what ensures that the results from an FMA scan are trustworthy and repeatable, no matter who's holding the scanner. It's really the foundation of trust for the whole system.
And believe me, this isn't just a friendly suggestion, it's an absolute mandate. This quote from the code itself makes it crystal clear. Every single examination shall, and that's the key word, be performed according to a detailed, written procedure. That kind of formality is what guarantees safety across the entire industry.
So what that means is, before a single sound wave even enters the steel, there is a ton of prep work. You can honestly think of it like a pilot's pre-flight checklist. Every single detail has to be checked and double-checked to make sure the scan is going to be perfect. This table here gives you just a tiny peek into the insane level of detail we're talking about. The standard lists out dozens and dozens of variables. Some, like the exact software version or the weld dimensions, are called essential. If you change one of those, you have to re-qualify the whole procedure from scratch. Others, like the specific brand of coolant gel, that goop they use to get a good contact for the sound waves, are non-essential. It's that level of rigor that makes the final result so incredibly reliable.
Okay, right. So you've got your super detailed procedure all written out. But what about the machine itself? How do you actually prove that your fancy, expensive ultrasonic equipment can even find the tiny flaws it's supposed to be looking for?
You use one of these, a calibration block. It's basically a standardized chunk of metal that has a bunch of perfectly made artificial flaws built right into it, like those little notches and holes you can see. Before you can inspect the real weld, you first have to prove that your system can find every single one of these known flaws on the test block. If it can't, it doesn't get used. Period.
All right, the procedure is certified, the equipment is perfectly calibrated. Now, finally, we get to the scan itself. The inspector is ready to capture the data that's going to tell us what's really happening deep inside that weld. And the process itself is very systematic. It's simple, really. First, you calibrate the system using that block to prove it's accurate. Second, you perform the scan on the actual weld, collecting that huge, rich matrix of data. And third, you generate and then analyze the image that comes out. It's a very methodical journey from setup to the final answer.
So what's actually happening during that scan? Well, the sound waves are taking all sorts of different paths. Some go directly to a flaw and bounce straight back, but others take a longer route, like bouncing off the bottom surface, the back wall, first. By capturing the echoes from all of these different paths, FMC builds a much, much clearer and more complete picture than you could ever get otherwise.
Capturing all that data is obviously a huge step, but we're not done yet. The final and arguably most important phase is turning that raw data into a clear, actionable, and permanent record of that weld's health.
Because this is where the human expert is absolutely essential. A trained and qualified inspector has to sit down, analyze these high-res images, identify what they're seeing, and then document everything with the exact same level of rigor that went into the scan in the first place. The final report is just as critical as the data itself.
And when I say they document everything, I mean everything. The standard requires all the stuff you see here and more. The exact machine that was used, the weld's unique ID number, the details of the calibration, the software version, and of course, a full breakdown of any flaws that were found, including their precise size and location. This creates a permanent, traceable record for the entire life of that component. So when you put it all together, you take the advanced FMC technology and you combine it with these incredibly rigorous ASME standards, what you get is a hidden pillar of our modern, safe world. It's this unseen process that's working in the background, making sure the bridges we cross, the planes we fly, and the power we rely on are all secure.
This is the amazing tech keeping us safe today. But it really makes you wonder, right? As we keep building bigger, taller, more complex things, what's the next great leap forward going to be? What are the innovations being cooked up in labs right now that will become the new, unseen guardians of our safety tomorrow?